All right, let's talk about the unsung heroes of our modern world, the electric drive. These are the hidden brains controlling the incredible power of electric motors that are, well, pretty much everywhere. Let's dive right in.
I mean, think about it. You've got electric motors in cars, robots, elevators, you name it. But if you just plugged a motor straight into a wall socket, it would just run at one crazy, uncontrollable speed. So how do we get that smooth acceleration in an electric car or the pinpoint precise movements of a factory robot? That's the big question, and the answer is the electric drive.
So here's how we're going to break it all down. First, we'll cover what an electric drive actually is. Then, we'll look at the classic way to control DC motors, and after that, we'll tackle the much bigger challenge of AC motors. We'll get into some really cool stuff called vector control. And finally, we'll wrap it all up with why this technology is such a massive deal today.
Okay, so first things first, what exactly is an electric drive? Let's get to the core of it.
You can think of an electric drive as a super intelligent power modulator. It's kind of like a sophisticated dimmer switch for a light, but for a powerful motor. It doesn't create new energy, it just takes the raw electricity from the grid or a battery and shapes it perfectly to tell the motor exactly how fast to go and how much force to use.
The whole system is actually pretty simple when you look at it like this. You start with a power source and you end with the mechanical load. That's the actual work getting done. But the real magic, the secret sauce, happens right in the middle, at step 2. That power converter, that's the drive. It's the brain of the whole operation, taking our commands and translating them into the precise electrical signals the motor needs.
To really get how we control motors today, we have to look back at the original workhorse, the DC motor. For a long, long time, if you needed to change the speed of something, DC was your only option, mainly because controlling it was, relatively straightforward. With DC motors, you basically have two main knobs to turn. First, you've got armature control. The armature is the part that spins. Think of this one like your car's gas pedal. The more voltage you give it, the more torque, or turning force, you get. Simple. The second knob is field control. This changes the strength of the stationary magnetic field inside the motor. This is more like shifting gears. You can weaken the field to let the motor spin a whole lot faster.
And this is where modern DC drives get really cool. It's not just about go forward. This table shows the whole picture. Quadrant 1. That's your standard forward acceleration. Positive speed, positive torque. But look over at quadrant 4. The speed is still positive, but the torque is negative. What's that? That's braking. The motor's actively slowing things down. Quadrants 3 and 2? Same deal, but for going in reverse.
And this isn't just braking where you turn all that momentum into waste heat. No way. This is regenerative braking. The drive is smart enough to turn the motor into a generator, taking the machine's momentum and sending power back into the battery or the grid. This is literally what happens in an electric vehicle every single time you take your foot off the accelerator.
Now, DC motors are great for control, but they have these things called brushes that can wear out. The real titans of the industry, the most rugged and reliable motors out there, are AC induction motors. But they came with one giant challenge. Their speed is naturally locked to the frequency of the power grid.
And that really is the heart of the problem. If you plug an AC motor into a standard outlet, it's going to want to run it at a speed that's tied to that 50 or 60 Hz frequency. You can't just turn down the voltage and expect it to slow down nicely. So, to really control its speed, you have to invent a box that can create its very own AC power at whatever frequency you tell it to.
And that box is the variable frequency drive, or VFD. The way it works is just brilliant. First, as you see in step 1, it takes the AC power from the wall and rectifies it, turning it into DC. Then, in step 2, it smooths out that DC power using capacitors. And finally, the really clever part, in step 3, it uses a set of super fast switches to invert that DC power, chopping it up to build a brand new AC signal at any frequency it wants.
Now, this new signal it creates isn't a perfect, smooth sine wave like the one coming out of your wall. It's a bit blocky, a stepped version. We call it quasi-sine wave. But here's the thing, the motor doesn't really care. It responds to the fundamental rhythm of this wave, which lets the VFD control its speed with incredible precision, from barely moving all the way up to full throttle.
Okay, so just controlling speed is a huge step. But what if you need more? What if you need the raw, instant torque response of a DC motor, but you want it in that tough, reliable AC motor package? Well, that's where we get into some seriously advanced stuff, vector control.
The goal here is basically to get the best of both worlds. A vector control is a super sophisticated technique that uses a ton of math and lightning-fast processors to make an AC motor think and act like a high-performance DC motor.
So how in the world does it do that? Well, instead of just blasting the motor with a generic AC wave, a vector drive uses a complex mathematical model of the motor itself. It calculates exactly how to split the current it's sending to the motor into two totally separate components. And this is the absolutely brilliant part. Those two components directly copy the two control knobs we had on our DC motor. One part of the current is only responsible for creating the magnetic field, the flux. That's just like our old field control. The other part is only responsible for producing torque. That's our armature control. By separating them, a vector drive can demand an instant change in torque without messing up the magnetic field. It gives an AC motor absolutely mind-blowing performance.
So we've gone through a lot of the tech, but why does this actually matter in the real world? Well, the truth is, this level of control over motors is completely transforming our world.
That incredible precision we talked about, it's the backbone of all modern automation and robotics. The ability to just run a motor at the speed it needs instead of full blast all the time, that leads to absolutely massive energy savings. That instant torque response, that's what gives electric vehicles their thrilling pin-you-to-your-seat acceleration. Even simple things like gently ramping up a motor to start protects expensive equipment from wear and tear.
And if you look at this chart, you can see they are everywhere. A whopping 45% are in industrial automation, running our factories. A huge 25% chunk is in HVAC systems, making our buildings way more efficient. And that slice for electric vehicles, it's growing like crazy. From the pumps that deliver our water to the appliances in our homes, drives are quietly making everything work better.
So as our world keeps demanding more efficiency, more precision, and more power, the intelligence inside these little boxes is more important than ever. It really makes you wonder, with faster computers and smarter algorithms just around the corner, what amazing things will the next generation of electric drives make possible? Thanks for watching.